So bonding energy and interatomic spacing together determine the bonding in, or define the bonding in solids. And to describe this further with the example of an ionic bond, so when two ions, one of plus and one of minus charge, come close enough that they can start feeling each other, they have, as mentioned previously, an attraction energy between them, which results in an attractive force that pulls the atoms together. And the atoms at first don't feel very much repulsion. So the net behavior is an attraction at a great enough distance from each other. But as they approach each other, due to this attractive energy and the resulting attractive force, they start getting closer and closer, and they start repulsing each other after a certain distance between the two centers of atoms is reached. So the initial attraction is because one charge is plus and one charge is minus, and then the repulsion is because the electrons start getting too close to each other, and the negative charged electrons in the different atoms, or the different ions in this case, start pushing each other apart. So you might imagine that the atoms pull together until the electrons in the outer shell are nearly in contact or very close to each other, but the electron shells cannot really overlap. So to be able to push together the electrons, the ions, so that the electron shells overlap would require tremendous force, which wouldn't really happen. So here, the attractive forces are defined as plus or positive, and repulsive forces as negative. Now, this is not tremendously important, but it is important to see that they are both, they act in different directions. Repulsive forces pull away, pull apart the atoms, whereas attractive forces pull together the atoms. So the definition, the signs have to be opposite each other. Now, the repulsive forces develop essentially when the proximity or the distance between the atoms is very, very small, or the outer layers. So this graph, similar to the energy versus interatomic spacing graph that we had seen, represents the force versus interatomic spacing. Here it's shown with the letter X. This is the same as the letter R. It doesn't matter, so don't be confused. So X naught here represents the position where the energy previously defined is minimum, hence the bond is stable, hence the force here, the net force, shown also as total force, is 0. The fact that the total force is 0 means that the attractive and the repulsive with different signs can be added to give a value of 0. So this x naught distance kind of corresponds to, very closely corresponds to, the summation of the radius of one ion and the summation and the radius of the other ion. So if you were to find the radius of the sodium +1 ion and the chloride -1 ion, and if you were to look at their ionic radii in a book, and then if you were to separately look at the distance of a single sodium to chlorine, sodium chloride ionic bond, you would see that the values are quite similar. So nearly touching of the outer electron shell, hence the volume of the two ions, is the condition of stability. You see also here certain things and details of certain details that you need to grasp. One of these is that the repulsive force starts deviating from 0 and growing rapidly in the case of this ionic bond, at a distance that is smaller, in interatomic spacing or interionic spacing that is smaller than the distance at which attractive force starts developing. So attractive force is essentially zero if you have sufficient distance. So if you have an atom here and then another atom in a location a kilometer away, the two atoms won't feel each other. As the atoms start approaching each other, there will be a point, a separation after which the attractive force becomes noticeable. Then this will pull together the atoms until the distance between them is small enough that a repulsion happens, but still the attractive force is greater in magnitude or in absolute value. Hence, the net force is still positive. But then soon afterwards, the net force will start to drop and will drop to zero. Beyond this point, if you were to try to push the atoms together, trying to overlap the two volumes of the atoms, you would see that the net force would be tremendously repulsive, meaning at this point, for example, you would be resisting this much force. So you would need to apply this much force at this spacing value to be able to keep the two atoms overlapped. So it is possible to push the atoms together, but because this slope of the net or total force curve is so great that it becomes more and more difficult to keep to push the atoms together. Hence, there comes a point where it becomes not possible. So this concept sort of could remind you of what you might have seen in perhaps high school or earlier classes, where if you have Coulomb's law and you look at how Coulomb's law describes the interaction between two charged objects, in this case Q1 and Q2, the two charged objects interact with a force between them that is related with the charges of either object and the square of the distance between the two objects and some sort of constant, what's called the Coulomb constant. So the idea here is that depending on what the charge on the object is, you might liken this, you might find this to be similar to a positively charged ion and a negatively charged ion with a particular charge, +1, +2, -1, -2, etc. And the distance between the two ions and some sort of constant in this particular case, that all lead to a force that can be calculated between these two charged objects. So the force equation, the force curves seen here, in fact, have equations that are similar in a sense to that which we had which we just showed and which you'd seen in earlier classes. So the attractive force decreases the interatomic spacing and pulls the atoms together, and it is inversely proportional with x, meaning it is increasing with decreasing x, or it is increasing with the atoms getting closer and closer. So this makes sense because the atoms being closer together feel each other more. The repulsive force is similarly inversely proportional with x, but it is to a higher power of x than Fa, meaning it still grows, increases as x decreases, but it increases more rapidly. So what this means is the slope here is greater than the slope here. And the total force is simply Fa plus Fr. And when Fa is equal to Fr, equilibrium is reached. Hence you have x equals x naught, or r equals r naught from the previous slides. And this is known as the equilibrium spacing. And this is a very specific distance. It's a characteristic distance for a given pair of atoms or ions. So if you have one sodium ion and one chloride ion, Cl minus, the two will always be at a specific distance. This will be a value on the order of a nanometer, so a very small value. And the distance referred to is, again, the distance between the two centers of the atoms. And it will be, as I said earlier, very similar to the summation of the two individual ion radii. And to move from this distance, either in the positive x or the negative x direction, hence to compress or to stretch this bond, or to lengthen this bond, or to shorten this bond, you need a large amount of force. And this is related with the slope of the net or total force curve here. So to move in this direction, you would need to apply force related with the slope here. And in the opposite direction, you would need to apply force of opposite sign, but related with the slope here. So the greater this slope at equilibrium, the more resistant the material will be to changing its bond length. So because of this, it is possible to assume that atoms are hard spheres or hard balls that come into contact. So when they're bonded, they are in contact, and pushing together these assumed hard spheres is not possible because they can't overlap. And pulling them apart is possible, but not easy and requiring force. So the bonding energy that we'd seen earlier is related to force, just as in earlier physics classes, through the relation seen on this slide. So the potential energy between two atoms is described as the integral of the force dx. So you might think of force applied over a distance. So a known force of 1 Newton applied over a distance of 1 meter while pulling an object is related to energy or work. Hence, you see that the summation of force applied over a range of x values gives you the energy. So for an atomic system, the net energy is generally described from infinity, a value of infinity for x, until a specific value for x. So you might think of this as, again, on this graph, infinity is in the plus x direction, and a value of x is at any random point on this on the horizontal axis. So from infinity to a value of x, f times dx integrated gives you the energy required for this distance to be covered by the two atoms, for this much separation, or this much coming together taking place. So this becomes, so F can be described, or F net can be described as Fa plus Fr, and X can be substituted for a particular value along the x-axis, such as the important distance of x naught, the bond stable length. So what this means is the net energy is the integral of Fa plus Fr dx from infinity in the plus x direction to the x naught position, distance. And what this translates to is that if you were to separate these and separately take their integrals, you'd see that En is equal to EA plus ER at any point, just like Fn is equal to Fa plus Fr. So the force versus X curve, the area under this curve, shaded or colored blue, from x equals infinity to x equals x naught, is defined by the integral from infinity to x naught f dx. So this here is the definition, or this area in blue is what this right-hand side of this equation represents. And this is the energy here described as bond energy that you need to provide to an atom pair with this separation between them, or to an ion pair with this separation between them, to move from this point to infinity. So if you were to change this x naught value to something here, the integral would cover only part of this area, and it would only describe the energy needed to separate the atoms from this distance. So x naught here is of importance because it represents some sort of stable condition. And as seen earlier, so if you were to take the function for this force, attractive force curve, and this repulsive force curve, and if you were to take their integrals according to this equation, you would see that they would give you an attractive energy and a repulsive energy curve. And the summation of the two would allow you to calculate the total or the net energy curve. So here, energy is represented often also by the letter U, not just the letter E. There are reasons for this, because we, in this class, or in material science, certain letters are used for different things, so it's different concepts, so it's define different different things. So don't be surprised if you see the letter U used for energy as opposed to the letter E. So the net energy curve, because of the function shapes of the forces and the resulting function shapes of the repulsive and attractive energies, the net energy curve has an energy minimum, which corresponds to the position, the spacing, the x naught value that is that corresponds to F net equals 0. So the shape of this curve, energy versus x, and the depth of this energy trough, or the absolute value of energy here, the energy needed to be given to the material to break it, depends, of course, on what the material is, what the two ions or atoms are, and the type of bond between them. So again, a stronger bond has a deeper energy trough or a well, and a weaker one has a shallower one. And again, many real-life properties depend on these. We had discussed thermal expansion, or coefficient of thermal expansion, and melting point earlier. And there are various other properties that get described in this course, such as hardness, modulus of elasticity, or conductivity, that can also be related with the shape of this E versus X curve. Of significance among these is what will later be described as modulus of elasticity. So modulus of elasticity is some value, some number that describes how easy or how difficult it is to lengthen or shorten a given material under an applied force. So the modulus of elasticity is kind of similar to the thermal expansion coefficient, but it is used for mechanical loading. So for physical, for loading, for pushing and pulling loads applied to the sample. And this at the atomic level is related with the slope of the force versus x curve, which is dF over dx, at the value of x naught. So what this means is here on this curve, the slope here is related with how easy or difficult it is to stretch or compress a material by pulling or pushing. Now, you might quickly see that the greater the slope, the more you will have to move in the force, along the force axis, to be able to move one unit along the x-axis. So because of this, the slope here is related not only for this particular bond, but through a collection of bonds in a real material, it is related with the actual real-life difficulty with which the material will change its length along the applied force direction. And to show a few examples of how some of these properties, sort of to prove that these properties stem from this curve or stem from the same parts of the curve, you can see that on the top left graph, linear expansion coefficient, this is thermal expansion because it's described as being, here it says degrees centigrade to the -1 power, meaning per degree centigrade times 10 is how you interpret this. So this point, this value means 200 200 per degree centigrade as a value of the linear thermal expansion coefficient. And when you look at this graph, objects with higher melting temperatures or materials with higher melting temperatures are going to be stronger, hence more difficult to change the shapes of via physical force or via thermal energy. So small coefficients of thermal expansion will correspond to high melting temperatures and vice versa, whereas high coefficients of thermal expansion, meaning easy to change the length of the bond or the object made of those bonds, will correspond to lower melting temperatures. Now, however, at a given melting temperature, you will also see that the value can change. And then you see that materials belonging or bonds belonging to a certain category, so the ionic bond of cesium chloride or sodium chloride or magnesium oxide, follow along a general line which could be described as the line for ionic materials, or in this case referred to as binary compounds because they have more than one type of atom. And when you have metals, you see that you have a different line. And for glasses here, you are given, without any particular examples, you are given a different curve. So this is not the only thing to look at, this energy versus X curve, but it is a major factor in determining the properties, a given property of a real material. So then when you look at the mechanical equivalent of coefficient of thermal expansion, modulus of elasticity, in some units that get described later, not relevant now, versus melting temperature, you see that at higher melting temperatures, say here for tungsten, you have a higher modulus of elasticity. Modulus of elasticity here was described as the slope at x0. Hence, it has the highest slope at x0, indicating that it is the hardest to change the shape of by applying force. The easiest to change the shape of corresponds also to the lowest melting temperature. Now, the reason why you have a very nice line here is because all of these are examples of metals and are all metallically bonded. If you were to choose some examples of ionically bonded materials, such as the so-called binary compounds, you'd see that there would be a relationship, but it would be along a different line. And there are certain factors that affect atomic radius. Now, atomic radius is of importance because, as we said, the bond length at x0, the value of x0 is almost equal to the value, the summation of the two radii of the two atoms forming the bond. But you might imagine that this bond length, or the atomic radii that result this, are dependent on certain factors. So some of these are factors that are permanent, and some of these are factors that are temporary. So as a temporary factor, you have temperature. So as temperature increases, the atoms are energized, and because of this, they vibrate more, and because they vibrate more, this x0 distance increases. The x0 increase can be thought of as looking at the energy versus x curve. You move up along the curve and in the positive x direction, hence x0, or the stable condition, sort of increases. Or you can think of it as the atoms get energized, hence their radii increase, hence the summation of the two radii and the bond length increases. Another factor is ionic value. So an atom might form an ion with more than one charge. So it can have a charge of 1 or 2 or 3, depending on the atom. So if, for example, it gets charged to +2, in the case of iron, its diameter, or its radius, or its volume shrinks, gets smaller compared to its neutral case, Fe. And if it gets charged to a higher value of 3+, where it has lost 3 electrons compared with its initial uncharged or neutral state, Fe, then it will become smaller and smaller. So here you see that the radius of the iron atom is 1.124 nanometers, and for Fe2+, it is significantly smaller, and Fe3+ is slightly smaller than for Fe2+. Now, if, depending on your material, if iron is in contact with a different atom and makes a bond when it is in a +3 state, then the distance between the two atoms, this charged iron ion and the neighboring ion, would naturally be shorter than when there's less charge, or when there's a neutral, well, when there's less charge on the ion. Another important factor is how many neighbors you have. Now, here in all of these cases, until now, we've discussed that you have one atom and one neighboring atom. So you have two atoms pulling each other along a line, which is the x-axis, the +x value we were discussing. So when you pull or you push, you are only moving linearly. Now imagine in the case of H2O, you have a central oxygen atom and you have hydrogen atoms, and you don't only have one OH bond, one oxygen and one hydrogen pulling or pushing each other, but you have one oxygen being pulled and pushed by one hydrogen on one side and another hydrogen on the other side. So depending on how many surrounding atoms there exist, the interactions, you might sort of imagine that the amount of energy that you can give to each relationship changes depending on the number of such relationships that you have to develop. So the interatomic distance increases due to repulsive forces developed by electrons when the number of surrounding atoms around a bond increases. So you can think of it as such. When you have one, only on one side of an atom, you have another atom. The ability to pull or push that neighboring atom will be different than if you have two neighbors on either side. So then, depending on the overall arrangement of atoms in a material, the atomic radius, hence the resulting bond length, hence the resulting strength of the bond, or the energy needed to break this bond, will be affected. And covalency is yet another factor. When you share electrons, as the number of shared electrons increases, so you can share one electron, you can share more than one electron, the atoms will attract each other differently. So when it increases, you will have more to share and there will be a greater attraction, and the radius will decrease and the bond will get shorter and essentially stronger. So to conclude, let's show a numerical example of a hypothetical bond between two materials, two atoms, that and the relationship between the two atoms is shown by this equation. The letter U represents energy. So energy is related with something plus something else. We look at the format, it says it's A over R to the M. M is given a value of 2, N is given a value of 10. So you might immediately imagine that because N is greater than M, this is the repulsion energy. This is E repulsive, and this is E attractive. A and B are just values that are related with what actual ion is being discussed. So this could be, for example, a value for sodium +1, and this could be a value for related with so they could be actually both are related with both ions. So the constants A and B are constants that have units that allow this right-hand side to be able to have an overall unit of energy to be able to balance the left-hand side, an energy unit in joules, and the values are related with the individual ions being attracted or repulsed, and the charge on those ions, and the sizes of those ions. So the value, if you were to go from sodium chloride to potassium chloride, because one of the ions would change in size, then here the energy equation would change, and the constants would have to change accordingly, so that you could get a different energy well, or an energy minimum at the equilibrium R value, or at the stable interatomic separation for this new pair of ions. So here, the interatomic distance is given, set to be given in nanometers, or 10 to the -9 meters. And the constants, the units are not physically meaningful, But when you plug in the values of the exponents, 2 and 10, then this gives you joule nanometer squared divided by nanometer square, hence joules. And this is joule nanometer to the 10th power divided by nanometer to the 10th power, which is again joules. Joules plus joules gives you joules. This is the same joule as in high school physics, but this is described at a small scale. Hence, you have very small values that will actually form. So 1 joule is quite significant in magnitude, in what it represents, and one single atom pair is not bonded very, very strongly together. But when you have millions of atoms, they form up, they come together to give you values that you're more accustomed to from other courses. So you plug in the values of the constants and the exponents, and you see that this is the equation. And the question says, where is the bond more stable, the most stable? This implies that the question asks where the energy is minimum. And the value, the answer to where is the value of R, and the R0 value is being asked. This could be asked as where is the energy minimum? It could be asked as where is the bond, at what value of R is the bond most stable, or it could simply be, it could simply ask, give the value of R naught. All three of these would mean the same thing. And then it says calculate the net energy at, it doesn't say it, but it means at this value. So essentially it wants you to calculate the amount of energy needed to break this bond. So we can remember a relationship that the energy is a minimum at R naught. So the value of du over dr that corresponds to 0 is going to be the slope of u versus r, the energy versus r curve, and the slope being 0 is going to give the minimum value. Hence, the r corresponding to that is going to be the r naught value that we're in search of. So the equation here can be rewritten as such. If you take the derivative with respect to r, you'd see that you get minus m times a to the r minus 1, minus m minus 1 power, etc. And by plugging in the values provided in the equation for this specific atom pair and equating this equation to 0 and solving this for the value of r that gives 0, we see that r equals 0.299 nanometers gives us, in this equation, a value of 0. So what we have done is we have taken the derivative of the equation for energy with respect to r and equated it to 0 and calculated or determined the value of r that gives du over dr equals 0. If you were to plug in a different value of r, you'd see that you get a different value of energy that would, and you would get a non-zero value of du over dr. So once you're able to calculate r equals 0.299 nanometers, you could ask yourself, am I going about this correctly? Does this make sense? So the amount of energy here doesn't make sense to us. We can't feel whether this is right or wrong, but this says the distance between the two atoms' centers is about 0.3 nanometers, and we know that one atom is about 0.1 nanometers in size. So the two radii combined, which is the value of r naught, could be on the order of 0.2, 0.3, 0.4, 0.1 nanometers. So if you here get a value of something like 3 nanometers, it would be kind of high. It would be too high. If you get a value of 0.001 nanometer, then it would be too low. So something on the order of this value would be reasonable because of our knowledge that one atom is about 1 angstrom in diameter, and 1 angstrom is 0.1 nanometers. So then you should have something close to that value. And then by plugging in this R value, which is the R naught value actually, into the initial equation provided here in the question, we can calculate the amount of joules, or the amount of energy, needed to be provided to the bond to break this bond. The reason this is called U min is because this is the value of R0. And the actual value here is in joules, hence it would make sense that you have 10 to the minus 19. You can't really tell if it's supposed to be 19 or 15 or 25, but you know it can't be 10 to the minus 1. That would be too high for a single atom, because what this means is when you compare how big a joule is from other experiences, other classes, to break a bond, if you claim that you needed to apply 1 joule, that would be way too strong. Because joule is sort of meaningful in the real world where you have millions and billions of bonds. So when you break a real material, you're actually breaking billions of bonds at the same time. So each of those bonds should probably not require too much energy. But when you get them together, when you collect them together, they start becoming as strong as what you're accustomed to in other physics courses. The fact that this is negative stems from the equation and from the given coefficients, but this always has to come out to be negative with the chosen notation, with the notation that we've adopted, because we describe energy as being a minimum and the stable condition happening at this energy minimum. Now, as I said, actually pluses and minuses could be interchanged as long as you're consistent, but it makes sense that energy is minimum because here, whether you supply heat energy or whether you supply mechanical energy, somehow you need to supply energy to a system that's stable to be able to break it. So at this point, it makes sense that you need to supply 6.4 times 10 to the minus 19 joules to this bond in form of heat, in form of mechanical pulling, pushing, or in form of something else to break this bond. And this curve, energy, potential energy versus interatomic distance, represents what we showed using numbers on the earlier slides. So if you were to take this side, which I said is the attractive side, or the attractive portion of the attractive energy equation, which I know because it has a smaller slope and a smaller inverse relationship with R. If you were to take only this attractive energy portion and plot it, you would get the attractive energy curve in blue. If you were to take only the other portion, the repulsive energy portion, you would get the curve in black, and the net energy curve would be the summation of these at every point. Here you see that the value of repulsive energy after a distance of something like 0.4 nanometers is nearly 0. Hence, the attractive and the net energy curves essentially overlap at distances greater than 0.4 nanometers. At values of R smaller than that, the net energy deviates from the attractive energy because the repulsive energy starts growing. Beyond a certain distance, on the other side of the R0 value of 0.299 nanometers that we calculated earlier, you will see that eventually the net energy curve starts resembling the repulsion energy curve because it grows much faster with a greater slope than the attractive energy curve. Hence, If you were given these two, if you were given this information, and if you were to plot this energy equation, or if you were to plot separately the attractive and the repulsive energies, you would be able to solve the question, find R0 approximately, and calculate the net energy that corresponds to that approximately. So the way to do that would be you would plot the black and the blue curves, and then at every R value you would sum them and find the net curve, and you would plot the net curve, and the value that corresponds to corresponds to minimum energy here would be your R0 value. And you would see that it would be about 0.3 nanometers. And our calculation here showed that it was 0.299. Of course, graphically, you wouldn't be able to easily determine such an exact value. The minimum energy that we calculate as minus 6.4 times 10 to the minus 19 would also be approximately possible to calculate by taking, say, each of these data points, but it would be, of course, quite cumbersome.